So today's objective is we are going to see the cosmic hierarchy, regular grammar, and we are going to see the unrestricted grammar, and we are going to see the context sensitive language CSL, and at the last we will see post correspondent problem. And today this is the last topic of your syllabus. um, all the best. So let's start the topic. First one, cosmic hierarchy is, according to cosmic hierarchy grammar, are divided of four types. Already we discussed this cosmic hierarchy in the previous videos, in the previous unit. So first one is a type 0, second one is a type 1, third one is a type 3, and the fourth one is a type 3. So what is type 0? Known as unrestricted grammar. What is this? Unrestricted grammar. And what is type 1? Known as context sensitive grammar or language. Whenever we say type 0, that is unrestricted grammar. Whenever we say type 1, that is a CSG, context sensitive grammar or context sensitive language. Type 2 known as context free grammar, and the type 3 is a regular grammar. So these are the four types are there in the cosmic hierarchy. Okay, first one is type 0, second one is type 2, type 1, type 2, and the third type 3. These four are there. First one is a unrestricted grammar, and second one is a context sensitive grammar, and third one is a context free grammar, and the fourth one is regular grammar. Okay, when you see the diagram you will easily understand. See, this is a type 3, as we have done here. F finite state machine, FSM, already we have done that. So this is called regular grammar accepted by finite automata. Okay, and what is type 2? Type 2 is okay, we will come from here. In here in the type 0, 1, 2, 3, but we will go from the down type 3 because already we have completed this in the second unit. Regular grammar. Okay, regular grammar accepted by finite automata. Type 2 is a context free grammar except by pushed on automata. Okay, with the help of pushed on automata we will solve this. And type 1 is a context sensitive grammar accepted by linear bond automata. Okay, this also will come under in pushed on automata. And type 0 unrestricted grammar is recognized by Turing machine, but you cannot decide, because of that it is unrestricted grammar. So that is recognized by Turing machine. It is not accepting, it is not a decider, it is a recognizing. Okay, it is accepted, and this is accepted, but this is not a accepted, this is recognized by Turing machine. So this is a cosmic hierarchy. Whenever in whatever the unit you will get this cosmic hierarchy, you can draw this all the diagram in the same way. Even if it is in the 5th unit or the 2nd unit or 3rd unit, if it is asked this, then you need to draw and explain. So the first one is type 0. What is type 0? In type 0 grammar include all formal grammars. Type 0 grammar language are recognized by Turing machine. We are telling recognize, we are not telling accept. Okay, unrestricted grammar or undecidable grammar is only recognize, it will not accept. These languages are also known as the recursive enumerable language. In the previous video, in the previous lecture, I told you recursively enumerable language. Okay, what will happen in the recursively enumerable language? In the recursively enumerable language, it will accept all the string what is available in the language L, grammar L, but uh, and rest of the string which is not in the language, that will be removed. Okay, and it will not give result for acceptance and rejectance. Sometime maybe or may not be which symbol is not available in the language. For that, it may give the result, or may it give the acceptance or reject, maybe. Okay, and what is the example for this? SAB is a BA, A is S. Type 0 example is SAB is BA, A is capital S. Okay, next. So this example is like we cannot solve this. So here type 1 context sensitive grammar. This type 1 grammar generate the context synthetic language. The language generated by the grammar are recognized by the linear bound automata. Okay, and what will happen in the type 1? First of all type 1 grammar should be type 0. All type 1 grammar should be type 0. For example, S is a AB. In place of AB you can write this and this. Terminals are there and you can solve this. Context sensitive grammar. The grammar will accept or reject. Okay, accept or reject. So this is a type 1. So what is the condition here? The first of all type 1 grammar should be type 0. Type 1 grammar generate the context sensitive language. The language generated by the grammar are recognized by linear bound automata. Okay, so this is about the type 1. If we go to type 2, the type 2 grammar generate this context free languages. The language generated by the grammar is recognized by a push down automata. Type 2 grammar generate the context free language. What it will do? It will generate the context free grammar or context free language. Type 2 grammar, this type 2 grammar generate the context free language. First of all, it should be type 1. First of all, it should be type 1. Left hand side of production can have only one variable. Left hand side only one variable. See, 1 2 3. Okay, so this is a type 2 context free grammar. Already we saw in detail about this context free grammar in the previous videos. Okay, and the last one is type 3. In the type 3 is a regular grammar. Type 3 grammar generate regular language. These languages are exactly all languages that can be accepted by a finite state automata. Type 3 is most restricted form of grammar. Type 3 should be in the given form only. V of VT multiply or T star. T star V or T star. So in this format only, in this form only, we can say it is a regular grammar, or we can say in place of regular grammar we can say type 3. Okay, now we will move to PCP, post correspondent problem. Okay, this we will see post correspondent problem. So this is also very important. So the post correspondent problem PCP introduced by Emil Post in 1946 is an undecidable decision problem. The PCB problem over an alphabet sigma is state as follows. Okay, so here for understanding the PCP we need to take some step we need to follow. So given the following two lists, we need the two lists. First one is M, second one is N of non-empty string over sigma. So this should be non-empty, at least some data should be available here. Next we have M, and in the M we have a string like x1, x2, x3 so on till n, and in the N we have y n, y1, y2, y3 so on till yn. So we can say that there is a post correspondent solution if for following if for some i1, i2 so on till I, where 1 less than or equal to ij less than or equal to n. The condition of xi 1 so on xi k is equals to yi 1 so on yin k. This is a satisfies. Okay, when we are saying y1 2 so on, so we can take some I value i1, i2 so on. In the same way, if we are telling non-empty string 1 less than or equal to ij and less than or equal to n, the condition is xi1 so on xi k is equals to yi1 so on yik is satisfied. Okay, so we will take an example. We will take the example, find whether the list. So in this in this the PCB we need to check the both M and N, and we should get the same result. Like take M is equals to ABB, AA, AAA. These are the strings, and N is equals to BBA, AAA, and AAA. Okay, so this is about the strings what we have now. So the solution for that, we have taken 1 2 3. So this is x1 x2 x3 y1 y2 y3. Okay, y1 y2 y3. So M x1, what is in M x1 is ABB. This is small ABB. This is small BBB. Small ABB. Okay, M of x2 is AA, M of AAA is x3. In the same way, N is BBA, N AAA, N AA. For the condition for this, you must have the same equal number of M and N. Example, how many are there? 3, 4, 5, 6, 7, 8. 8 symbols are there. In the dawn also we must have 8 symbol, and that should be 8. 1 2 3 4 5 6 7 8. Okay, So accordingly, in the PCB we will select any one of this, 1 2 3, anything you can select. So here in the here, for as per the example, x2, first we are taking x2. X2 is AA. First 2A is coming from here. Next is same n x2 AAA. Okay, you can take x2 or x3, is up to you. Whatever you want to take, you can take, but first letter should be same because we need to solve the problem. So here you can take x2 or x3, but you cannot take x1 here. So first I am taking x2, and the x2 x value is AA, and second one y2, from n it will become a y2. What is the value? AAA. In the above, first we got it yellow, and in here also in the first we got triple A, y2. Okay, this is x1 and x2 and y2, y1, and this is also y3. Okay, fine. So in the first step, yellow color is for step 1. In the step 1 I got the answer AA, this divided by this. Okay, next, this is a extra, the last one, this one is extra. Okay, and that is A, and now we need to check where is the A in the top. You can take either this or this. So I am going to take this one. Okay, I am going to take this one, ABB. First in the top one is ABB, and in the down BBA, in the down BBA, I got BBA. Again I am getting the extra here, B. When I am getting extra, I need to go, I completed this, and the last one is x3 and y3. Is it possible to add here? A is here and here also is A. Yes, that is a possibility. So in the last step, it will take from M, and this is taking from N. Okay, I got X and Y. Now equal, at the top and the bottom are equal, so now we need to stop. Whatever the data we have here, that we got it the answer. That means x2, x1, x3 is equals to y2, y1, y3. Okay, y1, y3. So how we got it this? Like first we have taken the 2, second one is 1, third one is 3. So here the solution, if you go like this, then you will get the solution. Okay, you can take first this, okay, then second you can take this one, or you can take this one, but first in the bottom should not be have extra. Okay, so this is about the thing, like you must take the x2 first, because in the bottom is more and at the top is less. So this is a solution for the PCB. Okay, post correspondent solution. Okay, take the another example. Find whether the list M is equals to, in the exam you are going to get the question like this. Find whether the list M is equals to AB, BAB, BBAAA, and n is equals to a comma BA comma BAB have a post correspondent solution. It is asking the question that is it a post correspondent solution. Same thing we need to do. M you need to write in the top, n you need to write in the bottom. But as I told you in the above example, m and n should be equal. See how many are there? 1 2 3 4 5 6 7 8 9 10. In the m it is 10. Next, a b a 1 2 3 4 5 6, only 6. At the above is 10 and in the bottom we have a 6. So this is, while seeing this also, we can say it is not acceptable. But we need to solve, we need to check the case. What we can take, okay, you can take any number, okay, you can go with x2 x3 x1 anything. So x2 x1 x3 does not belongs to y2 y1 y3. Length are not same. As I told you, the length of these symbols string is not equal. When it is not equal, hence it can be said that this post correspondent problem is undecidable. Without doing any operation like this, we directly can say this is undecidable. Okay, so this is about the example. Okay, I hope you understand this. This is very easy concept. Definitely you will get the question, definitely you will get question related to this. Okay, so this is 2 1 and 3. This is a answer. If you go in this way, we will get the solution. I hope you understand this. Thank you very much. This is our last lecture of ALC, means our automata theory subject, or automata language and computation. So thank you very much. If you have any kind of doubt, you can message me or you can call me, or if you have so many doubts, we can make a Zoom meeting with the help of two-way interaction we will do. Okay, thank you very much. We will see you in the coming classes if it is necessary. Okay, thank you very much.